Hi, and welcome to the second part of our stoichiometry topic. Continuing on from part one, where we looked at how we can read chemical equations and what it's actually telling us about the ingredients that we need for that chemical reaction to occur. So, knowing the stoichiometric ratios of equations, if we know the number of moles of one substance in a balanced equation, you can determine the number of all moles of other substances in that equation. So if we look at this reaction here, we can see that 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water vapor. So we have a mole ratio of 2 hydrogens is to 2 oxygens is to 2 waters. So using this mole-to-mole calculations ratio, it makes it really easy for us to work out if we need to form 7.5 moles of water, how many moles of oxygen are actually needed to form that 7.5 moles of water. So if we have a look at our reaction, it says if we look at it, compare our oxygen to our water, we need 1 mole of oxygen for every 2 moles of water to be produced. So if we require 7.5 moles of water, what we need to do is we need to have a look back at our ratio, and we can determine how many moles of oxygen we actually need. So as you can see here, our ratio is 1:2. So if we've got 7.5 moles, how many moles of oxygen will we need? All we have to do is to divide that 7.5 moles by 2, and that tells us that we will need 3.75 mole of oxygen to produce that much amount of water. Linking this back to our molar volume of gases, we can then take this one step further and we could work out what volume of oxygen gas we required to produce 7.5 mole of water. So using our molar volume equation, we can rearrange that. So the volume of oxygen is equal to the moles times the molar volume. We'll just assume we're at standard laboratory conditions. So the number of moles is 3.75. Our molar volume is 24.5. So that means we need 91.9 litres of oxygen to produce 7.5 mole of water. Let's have another look at another example. This reaction is with solids and gases. So if we react 4 moles of aluminium with 3 moles of oxygen, we produce 2 moles of aluminium oxide. So looking at that first question, how many moles of aluminium are needed to form 3.7 moles of aluminium oxide? So just like we did with the last question, we need to look at our ratio of aluminium to aluminium oxide. We have a ratio of 4:2. We want to form 3.7 mole of aluminium oxide. So we want to find out how many moles of aluminium are needed. And this is where we look at our mole ratios. We can see here that we have a ratio of 4:2. So to find out how much aluminium we actually need, we need to multiply 3.7 by 2. And that tells us that we need to use 7.4 mole of aluminium to produce 3.7 moles of aluminium oxide. And linking this with our other mole calculations, we can then convert that to find out the mass of aluminium that we require. So rearranging our equation, mass is equal to moles times by molar mass. We know we need 7.5 moles. The molar mass of aluminium from the periodic table is 26.98. Multiply that together and it comes to 199.6 grams of aluminium, but thinking about our significant figures, we can write this as 1.9 times 10 to the 2 grams of aluminium is required. The next question is asking us how many moles of oxygen are required to react completely with 14.8 moles of aluminium. So once again, we go back to our balanced chemical equation, determine what our molar ratio is, and we know that for every 3 moles of oxygen, we need 4 moles of aluminium. So we're given the information how many moles of oxygen are required. We have 14.8 moles of aluminium. So we're trying to find out how many moles of oxygen we actually need. So to work out this unknown value, we need to look at our mole ratio. So 14.8 moles of aluminium, we know that we need 4 moles of that. So if we divide that by 4, it gets us to 1 mole of aluminium. If we then times that by 3, that will tell us how many moles of oxygen is required for this reaction to occur. And so that tells us that we need 11.1 moles of oxygen gas to completely react with 14.8 moles. And completely react means we've got nothing left over. All the oxygen has been used up, all the aluminium has been used up, and it's all being converted completely to aluminium oxide. Looking at the last question on this slide, it's asking how many moles of aluminium oxide are formed when 0.78 moles of oxygen is reacted together. So we have 2 moles of oxygen is to 3 moles of 2 moles of aluminium oxide to 3 moles of oxygen. And we're trying to find out how many moles are formed. Okay, so looking at our ratio again, if we have 0.78 moles of oxygen, we need 3 moles in the balanced equation. So we divide 7.78 by 3 to get 1 mole. We times that by 2, and that gives us the number of moles of aluminium oxide that's going to be formed. And in this case, it's 0.52 moles. We can also do exactly the same thing with mass to mass calculations. So if we are given the mass of a substance and asked to work out the mass of something that would be produced, we'd do exactly the same thing, but this time, as per usual, we would convert our mass of substance to our moles of substance and work it out exactly the same way. And we'll be practicing those in class at some point, and I'll put a video up with the worked explanation of the answers at a later date. Thank you.